All right, so section 12.2, differentiation and integration of the vector valued function. So let's begin with the definition of the derivative. All right, so r prime of t is equal to the limit as delta t goes to 0 of r of t plus delta t minus r of t, both of those are vector valued functions, divided by delta t. Okay. For all t for which this limit exists. So if r prime of t exists, then r is differentiable at t. And if r prime of t exists for every t, for all t, in an interval, call it I, then it's differentiable on the interval. Okay, now when we differentiate vector valued functions, we really are differentiating each component function. Okay, so it does get differentiated on a component by component basis. Let's see. So differentiate on a component by component basis. And there's a great proof of this in your book, if you want to check that out. So if you've got r of t equal to f of t in the I direction plus g of t in the j direction plus h of t in the k direction, then r prime of t is equal to f prime of t in the I direction plus g prime of t in the j direction plus h prime of t in the k direction. And that is actually a theorem from your book, theorem 12.1. All right, so let's see an example of this. Okay. So my curve looks like this. And we have the point 0, 2, 1, 3. And so we're coming in here. So this is R1 from the origin. We're going right 1 up 3. So that's R of 1. And then R of 2 is taking us here from this point. We are moving right, it's in the x direction 1 unit and in the y direction 2 units. So 1, 2, it's putting us like right up here. And that's R prime of 1. Okay, so now let's go ahead and do another example. So example, I'm going to give you R of t is equal to cosine of t in the I direction plus sine t in the j direction plus 2t in the k direction. Very nice. All right, so our job then is to find r prime of t, r double prime of t, r prime of t dotted with r double prime of t, and then finally r prime of t crossed with r double prime of t. Okay, so let's find these. So r prime of t is going to be negative sine of t in the I direction plus cosine of t in the j direction plus 2 in the k direction. All right. Okay, now r double prime of t. Oh, forgot the little vector there. There we go. All right, so we take the derivative again, and we get negative cosine of t in the I direction minus sine t in the j direction plus 0 in the k direction. Then we need to find the dot product, so r prime of t dotted with r double prime of t. So recall, we're just going to multiply corresponding components and add them up. So that's negative sine t times negative cosine t plus cosine of t times negative sine t plus 2 times 0. So that's going to be sine t cosine t minus cosine t sine t, which is 0. Interesting. All right, and finally the cross product. So we have r prime of t crossed with r double prime of t. So that's going to be equal to ijk. Okay, and r prime of t was negative sine cosine 2. R double prime was negative cosine negative sine 0. Okay, and so then we'll do our cofactor expansion. So for the I component, we have cosine t times 0 minus 2 times negative sine t. So that's our I component. Minus, because it's the j component, minus negative sine t times 0 minus 2 times negative cosine t. That's our j component. Okay, and then I'll just add it underneath. Plus, in the k direction, we're going to have negative sine t times negative sine t minus cosine t times negative cosine t, and that's the k direction. So this gives us 2 sine t in the I direction minus, okay, so this is 0, and then minus 2 negatives makes a positive, so that stays negative, 2 cosine of t in the j direction plus sine squared t plus cosine squared t in the k direction. But we should all know that sine squared plus cosine squared is actually equal to 1. So this is 2 sine t in the I direction minus 2 cosine t in the j direction plus 1 in the k direction. And there is our cross product. All right. So let's define smooth. Okay, so for r of t equal to f of t, g of t, h of t, r of t is smooth on an open interval I if f prime, g prime, and h prime are continuous on I, and r prime of 0 is not, I'm sorry, r prime of t, fix that, r prime of t is not equal to 0. And that's for any t in interval I. Okay, so let's have an example of identifying where a curve is smooth. So find the intervals where r of t equal to, oh, that looks like an x. R of t equal to 5 cosine t minus cosine of 5t in the I direction plus 5 sine t minus sine of 5t in the j direction is smooth. Okay. All right. So where is it continuous? Oh, I forgot to tell you, we are only looking for this on t from 0 to 2 pi. So for 0 less than or equal to t less than or equal to 2 pi. There we go. Okay. So where is this smooth on the interval from 0 to 2 pi? Well, 5 cosine t minus cosine 5t are continuous functions, and they do have continuous derivatives. So f of t and g of t have continuous derivatives, so that's not a problem. Okay, so then we need to figure out where's r prime of t equal to the 0 vector. Oh, and I should make that very clear. This is referring to the 0 vector because r of prime of t is a vector. Okay. All right, well, the first thing we're going to need to do is find r prime of t. So r prime of t, we have, let's see, negative 5 sine of t minus sine of 5t chain on a 5. Okay, so that's my I direction. Okay. Plus, okay, now let's find the derivative of 5 sine t, that's a 5. 5 sine t minus sine 5t, so that's going to be cosine of t, 5 cosine of t, minus 5 cosine of 5t. Okay, and that's in the j direction. All right. So we have minus 5 sine t minus sine 5t times 5 in the I direction, and 5 cosine t minus 5 cosine 5t in the j direction. So now we need to find out where is this equal to 0, specifically the 0 vector. Okay, well, this is actually not going to be too bad for us. So we've got minus 5 sine t minus 5 sine of 5t equal to 0. And we have got 5 cosine t minus 5 cosine of 5t equal to 0. We need both of these things to happen simultaneously. Okay, so I'm going to divide out the negative 5 on the left-hand side. We have sine of t minus sine of 5t, plus sine of 5t equal to 0. Oh, I feel like that's supposed to be... Yes, it is. Okay, so you guys may have caught my error. This is negative cosine of 5t, so this should be negated as well. That should be a plus, so that should be a plus. There we go. That's better. Oops. So that should be a plus, which means this, darn it, keep hitting the wrong button, which means that this should be a minus. If I factor out a negative 5 and divide, go away. What are you doing? There we go. So this should be a minus there. Oh, good. That's going to make that so much easier to solve. All right, and then we've also got, I can divide the 5 here. So then I've got cosine of t minus cosine of 5t equal to 0. So really what I'm looking for is when is sine of t equal to sine of 5t, and when is cosine of t equal to cosine of 5t. Well, clearly t equal to 0 satisfies both of these conditions. All right, and then after that, it looks like we'll be looking at multiples of pi over 2. Okay, so, and the reason for that is because those are the places where multiplying by a whole integer, a whole number, is not going to affect the value as much. So sine of pi over 2 and sine of 5 pi over 2. Are these actually equal to each other? Well, sine of pi over 2 and sine of 5 pi over 2, those are coterminal angles. So yes, they absolutely are equal to one another. The same thing will be true for pi, and for 3 pi over 2, and for 2 pi. So at t equal to 0, t equal to pi over 2, t equal to pi, t equal to 3 pi over 2, and t equal to 2 pi. Those are going to be the angles from 0 to 2 pi where sine of t and sine of 5t are equal to each other, and cosine of t is equal to cosine of 5t. Okay, so these are the locations where the derivative is equal to 0, where r prime is equal to 0. So everything from 0 to 2 pi except for those individual locations, it's going to be smooth. So we are smooth on 0 to pi over 2. We don't need a union here. On pi over 2 to pi, on pi to 3 pi over 2, on 3 pi over 2 to 2 pi. There we go. So there are 4 intervals where this curve is smooth. And if you sketch this curve, you'll see that that is actually the case. It's actually called an epicycloid. So I'll go ahead and sketch it for you so you can see it. So it's going to look like this. And at these locations, we've got t equal to 0 here, pi over 2 here, pi, 3 pi over 2. And it actually looks kind of like this. It's kind of neat. It began right here when t is 0, and it goes around in this way. There we go. Okay, so now let's look at the properties of the derivatives of vector valued functions. Derivatives of vector valued functions. Now you're going to find that a lot of our regular derivative properties are going to carry right through here. There will be some slight differences simply because these are vectors that we're working with now and not just regular functions in general. So let r of t and u of t be vector valued functions. W of t be a regular function of t, be a regular function of t, very mathematical there, and c a real number. Then here's what we've got. Number 1, the derivative with respect to t of a constant c times r of t. Oops, yeah. That is just equal to c times r prime of t. Okay, so the constant is just going to come right out. Number 2, the derivative with respect to t of r of t plus or minus u of t. That's just going to be equal to r prime of t plus or minus u prime of t. Okay. Number 3, the derivative with respect to t of w of t times r of t. So remember, w of t is just a regular function. It's not a vector valued function. That is going to be equal to, and we're applying the product rule, w of t times r prime of t plus w prime of t times r of t. Okay, so you see the product rule there. Number 4, the derivative with respect to t of r of t dotted with u of t. Okay. That's going to be equal to, again, the product rule is going to pop up, r of t dotted with u prime of t plus r prime of t dotted with u of t. So once again, we see that product rule occurring here. We're going to say the same thing in the next one with the cross product. So number 5, d dt of the cross product r of t and u of t. It's going to be r of t crossed with u prime of t plus r prime of t crossed with u of t. Number 6, d dt of r of w of t. Okay, so here we have the chain rule happening. That's going to be equal to r prime of w of t chain on w prime of t. Now from Cal 1, we're used to writing a dot for the chain on, or at least I am, but make sure that we don't write dots here because the dot with vectors implies a dot product, but you can't have a dot product with a vector valued function and a regular function. It only works if you've got 2 vector valued functions or 2 vectors. And finally, number 7. Number 7 says if you dot r of t with itself, you are going to get a constant. But that implies that if you dot r of t with its derivative, you will get 0. And that's exactly what we saw earlier in our previous example. Okay, so let's do some examples using these properties. So example, let's have r of t be equal to 1 over ti minus j plus ln of t k. And let's have u of t equal to t squared I minus 2tj plus k. All right. Let's start off with part A here. Let's find d by dt of r of t dotted with u of t. Okay, so the formula for that tells us that this is going to come out to be r of t dotted with u prime of t plus r prime of t dotted with u of t. So we're going to need to know what is u prime and what is r prime. So let's go ahead and find those right quick. All right. So r prime of t, that's going to be equal to negative 1 over t squared I minus 0j plus, and the derivative of ln of t is of course 1 over t, k. All right. And u prime, that's going to be 2ti minus 2j plus 0k. Okay, so we are going to dot r with u prime. So that's our first step. So r dotted with u prime, that is going to be 1 over t times 2t plus negative 1 times negative 2 plus ln of t times 0. Okay. So that's r of t dotted with u prime of t. Now we dot r prime of t with u of t. So now I'm doing these two. First I did these two. Now I'm doing these two. So let me get rid of those arrows. They're mucking it up. Okay. All right. So u dotted with r prime, or r prime dotted with u, is going to be negative 1 over t squared times t squared plus 0 times negative 2t plus 1 over t times 1. Okay, there we go. So now we can simplify. So we get 2 plus 2 minus 1 here. The t squares will cancel one another. We know t is not equal to 0, so that's not an issue. Plus 0 plus 1 over t. So it looks like we're going to get 3 plus 1 over t. All right. Okay, next, part B. Let's find d by dt of u of t crossed with u prime of t. All right, so we're going to have to find that cross product first, and then we can find the derivative of that cross product. Okay, so this is going to be equal to the determinant of I, j, k, and u was t squared, negative 2t, and 1. And then u prime, I have to go back up here and get that one, was 2t minus 2, 0. Did I really need to go back up there and get that? I can do it right here. 2t minus 2 and 0. Okay. Now, we do our cofactor expansion, and we get in the I direction, negative 2t times 0 minus 1 times negative 2, I, minus, for the j direction, t squared times 0 minus 1 times 2t, that's the j direction, plus, and in the k direction, we have got t squared times negative 2 minus negative 2t times 2t, and that is our k direction. All right, so that's going to be positive 2 in the I direction minus negative 2t, so that becomes plus 2t in the j direction, plus negative 2t squared plus 4t squared in the k direction. Okay, so that's minus 2t squared minus negative 4t squared. All right, so that looks good. So this simplifies down to 2 in the I direction plus 2t in the j direction plus 2t squared in the k direction. So we were asked to find the derivative of this, u of t crossed with u prime of t. So that's d by dt of 2t squared, if I want to put it in component form. So that's going to be equal to 0 to 4t. So back into standard unit vector notation, we have 0 in the I direction plus 2 in the j direction plus 4t in the k direction. And there we have it. Okay, so technically speaking, because the I has a 0 component, we don't have to put it there. This is good enough for my money, but it's possible that your homework could get picky. So if there's an issue and it doesn't want the 0 component vector portion, you can just drop that off there. This is perfectly acceptable as well. And now on to integration of the vector valued function. Okay, so let's go ahead and define that right quick. If you have r of t, let me say if r of t is equal to f of t in the I direction plus g of t in the k direction, sorry, g of t in the j direction plus h of t in the k direction, okay, and f, g, and h are continuous on the interval from a to b, then the indefinite integral of r of t integrated with respect to t is equal to the indefinite integral of f of t dt in the I direction plus the integral of g of t dt in the j direction plus the integral of h of t dt in the k direction. Okay. The definite integral is, of course, let's just say and the definite integral is the integral from a to b of r of t dt is equal to the integral from a to b of f of t dt in the I direction plus the integral from a to b of g of t dt in the j direction plus the definite integral from a to b of h of t dt in the k direction. And of course, these also hold true in 2 dimensions. There's just no k component. If you just have the I and j component, it works exactly the same way. Okay, so just like with the derivative, we see that these are going to behave on a component by component basis. The integral is equal to the integral of each component. So let's do an example so you can see this in action. All right. So let's find the antiderivative of t in the I direction plus 3j, 3 in the j direction, dt. Okay. So we're going to integrate this on a component by component basis. So this is going to be the integral of t dt in the I direction plus the integral of 3 dt in the j direction. So that's equal to 1/2 t squared plus a constant. I'm going to call it c1 in the I direction, plus 3t plus another constant in the j direction. Okay. So this is 1/2 t squared in the I direction plus c1 in the I direction plus 3t in the j direction plus c2 in the j direction. Okay. So that's 1/2 t squared I plus 3tj. And then c1 in the I direction and c2 in the j direction is just some constant vector. And that's what we're going to add to these. We are going to add a constant vector. Now, I will tell you, I am very, very picky about you putting an arrow above this c. Okay, very, very picky. Let me put a nice, great big circle around it. Must add a vector c. It's a constant. I'll put constant up here. A constant vector c. Okay, because you're adding a vector. So we're doing this integration on a vector. The result is a vector. The constant term that would be added is also a vector. So you must make that a vector. I want to be very clear about that. Okay, but that's our final answer. 1/2 t squared. I'm still writing in blue. 1/2 t squared in the I direction plus 3t in the j direction plus some constant vector. All right, next example. Let's do one that's got 3 components. So we have an x, y, and a z component. So let's find the definite integral from 0 to 1 of the cube root of t in the I direction plus 1 over t plus 1 in the j direction plus e to the negative 1 in the k direction, integrated with respect to t. Okay, so this is a definite integral, so there will be no constant added at the end. We will calculate the definite integral. So let's see here. This is the integral from 0 to 1 of t to the 1/3 power dt in the I direction, plus the integral from 0 to 1 of 1 over t plus 1 dt in the j direction, plus the integral from 0 to 1 of e to the negative 1 dt in the j direction. All right, so the antiderivative of t to the 1/3 would be t to the 4/3 divided by 4/3, which would make it 3/4, and we'll evaluate that from 0 to 1 in the I direction. Plus, the antiderivative of 1 over t plus 1 is going to be ln of t plus 1, evaluated from 0 to 1, and that's our j component, plus the antiderivative of e to the negative 1. Now, don't let e to the negative 1 throw you. E to the negative 1 is a constant. There is no t there. So this is just going to be e to the negative 1 times t, evaluated from 0 to 1 in the k direction. All right. So this is going to be 3/4, 3/4 minus 0 to get 3/4, plus ln of 2 minus ln of 1, which is, of course, 0. That's the I direction. Don't forget your components here, j direction. Plus, and then we have e to the negative 1 times t, evaluated at 1 and 0. That's just going to be e to the negative 1 in the k direction. So this result is 3/4 in the I direction plus ln of 2 in the j direction. Should have put brackets around that. Plus e to the negative 1 in the k direction, or in component form, 3/4 ln 2 e to the negative 1. Okay, so put a box around those answers. And I think that's gonna just about wrap it up for this one. If you have any questions, as always, please just let me know. And yeah, that'll do it for this one.